Good afternoon, everybody. My name is Mirza Popovac from the Austrian Institute of Technology. And my talk today is on the compound wall treatment for complex turbulence flows. But before that, I have to first explain some background story because this compound wall treatment comes in a package with runs turbulence modeling, and for proper runs simulation of wall-bounded flows, one needs to model appropriately turbulent effects, and this means in the first place the near wall turbulent effects, and then to be able to appropriately treat the very near first cells near to the wall. In that respect, widely used are K omega or K and K epsilon family of Rans turbulence models, where in K omega family most widely established is the K omega SST variant, and this model and the variant is already available in open foam distribution, but the problem with it's fine-tuned to various flows, so it works for various flows, so everything is fine except for one thing, and that is the problem that turbulence modeling is somehow similar to the religion, where people believe in things regardless of the reality. And my confession is I'm a K epsilon man. So in K epsilon family of models, what is available in open form does not perform really satisfactorily. So therefore I had to go with my own. I will say a few words about the model K epsilon phi t f whatever, but I'm using something slightly different and performing better. But in either case, either you are in K omega or K epsilon branch, what I find somehow disturbing is this last bit where they explain you have to set the wall boundaries properly, and this I don't see very well done, and I will explain now why. The story goes something like this. So in two equation eddy viscosity approach, one models the turbulent stresses. Okay, you don't see this. The turbulent stress is modeled through eddy viscosity, which is the function of flow variables, which means one needs to solve equations, two equations in this case, to define this eddy viscosity. In K epsilon family, as the name suggests, these two equations are K, turbulent kinetic energy, and its dissipation rate epsilon. Apart from the fact that epsilon is completely modeled and therefore source of troubles, the problem with this framework is, as you see on the graph, plotted as symbols, is what eddy viscosity should be in the fully developed turbulent boundary layer taken from DNS, and the solid lines is what is defined from K epsilon. So away from the wall, it fits very well, but let's say near 10, y plus 10, you can see very pronounced this departure, and this deficiency people usually treat by dumping this turbulent viscosity, either through some ad hoc functions, or in better case, like Durbin suggested, by noting that actually the wall normal component of the turbulent fluctuating velocity is better scale velocity scale for this turbulent viscosity, and then you get this dashed line which fits almost perfectly to the DNS symbols. Apart from that, these are local viscous effects, this damping. There's also something related to pressure for turbulent fluctuations, and this is not a local effect, and therefore there have been proposed to include this through the elliptic relaxation function, for which he is solving Helmholtz equation. This is the second one to the right. And what I have been doing, I was solving this wall normal turbulent fluctuation component in the normalized manner. So it's I call it zeta in this case, and for F for blending function, relaxation function, I'm introducing this extra possibility with n zeta to adjust to zero wall boundary for this function in order to stabilize the simulation. This I will comment later then when we come to the results. In addition, there are constraints for length scale and time scale in this equation. And this set of equation now gives me good explanation of what's going on in the wall bounded turbulent flow. Here I'm coming to the point of my talk, and this is treating the near wall region. So in the wall-bounded flow, everything that takes place, everything important, takes place near the wall. 90% of variation is taking place in 10% of this thin boundary layer. So if you have your mesh fine enough that, again, you will not see with the pointer, that your first point is somewhere where the first arrow is located, then your velocity reconstruction will give you good approximation of the velocity in order to capture the wall shear stress. If you are not so lucky, if your center is far away, like in this fully developed profile type, then your velocity reconstruction fails miserably in predicting wall shear stress, and you have to use some pre-knowledge about it, and the pre-knowledge comes from the observation, both experimental and numerical, that there are two distinct layers can be identified in the boundary layer: the viscous inner flow and the fully turbulent outer layer. And then you can reveal universal behavior of this velocity distribution by using proper scaling. What is proper scaling for wall-bounded flows? Well, of course, wall shear stress. And then comes the question, how do you define the wall shear stress? If you are fine with your mesh, then it's directly from the gradient of the velocity, and if not, we are equating that with the kinetic energy, because we are assuming that actually these turbulent fluctuations, these turbulent tumbling is what results in the wall shear stress in the end. Okay, having that, just a quick note, there is of course a region in between viscous and logarithmic layer. This is buffer layer, and this one gives us a little bit of trouble. But how to get to my equation for a boundary layer? I'm integrating my momentum equation, assuming that the only variation is in the wall normal direction of the streamline of the streamwise velocity, and I'm linearizing this equation such that my terms related to the convection and the pressure gradient I assume to be known from the previous time step, and then I can assume that, like I said, in the viscous sublayer, only viscous effects are there, so I'm neglecting turbulent viscosity, and further away from this viscous sublayer thickness, I'm assuming no kinetic viscosity, only turbulent viscosity is dominant, and then integrating twice in the two regions and imposing smoothness constraint, I'm getting my constants and terms, and the final equation looks like so to the left, with, as I said, constant factors determining the non-equilibrium effects. What you don't see under the screen how over there is turning shear stress into standard log-law form, which is nice because we know that holds in the we have seen in the experiments. Only difference is this exactly the non-equilibrium factor psi. And in this case, I am expressing my wall shear stress as the velocity and the distance wherever it is, wherever the first near wall cell is located, times some effective wall viscosity, which I'm getting, as you can see in normalized units to the right. In case I'm in the viscous sublayer, it's kinetic viscosity. If it's further away, then it's my viscosity obtained from the log law. And this is then the key point. If you get to find the expression for U plus such that it boils down to viscous or this fully turbulent one in one go, then you simply have your effective viscosity defined for any case. And this is exactly what you get to do when you, for instance, define your boundary conditions for nu t. You say nu t is something like standard wall function or low Reynolds modification, whatever. You decide, you opt for one or another definition of exactly this U plus. And this is then the point of my talk. By taking harmonic mean of the higher moments, so treating these normalized velocities as higher moments, so not kinetic energy, but already power, in case of 3, you get actually very nice and smooth distribution of the viscosity of the velocity throughout the boundary layer. And not only velocity, but also the gradient also fits perfectly, which means I have algebraic expression for velocity and its gradient throughout the near wall region, independent of, not explicitly dependent on this thickness of the sublayer, or however you defined whether you are going for low Reynolds or standard wall function. And this is now the point. I'm using this expression in the one for viscosity there for whatever value I get, and I should get the correct viscosity, which results in the correct shear stress. And that's and that's the point of the compound wall treatment. So compound wall treatment, a little bit on terminology, is not a replacement for a wall function. It's unifying both approaches regardless of the mesh. If you are close enough, he boils down to the viscous one. If you are far away, then he simply neglects the first one, goes to the second, and you don't have to basically practically it means you don't have to type two separate wall boundary conditions for turbulent viscosity, but it's not just practicability of typing, it's really about physics, that he's reconstructing this in this smooth manner, which actually has some justification through this harmonic mean. So having these two, I can also construct my boundary conditions. Again, you don't see from the screen over there. For other turbulent quantities, k and zeta, these are basically fluctuating velocities, so on no slip wall these are 0. As I said, the relaxation function f, I can tune to go either to 0 or non-zero. This non-zero can cause some numerical problems, but we will leave this for later. We can tune from 0 to non-zero after the field is developed. And the only thing where I can use then left this blending is for the epsilon, which, as I said, now shows clearly that in the viscous layer I have this gradient which is close to 1, and further away it goes to 0. So you just use it as a weighting factor for all the turbulent quantities. and some validation. In my case, I always look at the plane channel flow, backstep, and the jet, because they represent they feature many wall-related flow effects. And as you can see, if I have fine mesh, I get my velocity distribution as the DNS is giving, and so on for other turbulent quantities. And when I'm changing just viscosity, effectively changing Reynolds number, leaving the mesh unchanged means I'm effectively moving it away. I am getting my profiles of the velocity to fit on the velocity line, and just goes further away. You can imagine that, for instance, in the orange line, this will be my first cell is y plus 50, blue cell is y plus 5000. So whatever down to 1, it goes with one expression equally the same. I guess I have to. Yes. In this case, I'm taking this backstep, which of course one needs to reproduce properly this recirculation and reattachment, and I'm not changing the setup. I'm just changing now the mesh, and I should get the same profiles as I am. But here, interestingly, of course, along this bottom line, if you are looking at y plus, you can see that it's changing. This is obvious because it's following the flow characteristics locally there. So in one go, you can have, by the nature of the flow, that your y plus for the same mesh is sometimes integration to the wall very close to 1, or further away, very far away from it. And in this case, in the jet case, I took it even one step further. I took deliberately very coarse mesh away, and just refined here around the stagnation point. And now, for once, the flow conditions are changing in the stagnation region. And for another thing, as it flows away, it gets to very rough mesh, and it should capture the flow features as it is. So this is how it looks compared to the reference cases. And now I'm comparing to what is available in open form. I'm comparing to K omega SST, as I said, because it works much better than this K epsilon phi t whatever. And yeah, you can see the differences are negligible, I would say. What one can see, and this is my target, I want to calculate my cases on such problems where geometry is very complex, where flow effects are various in various regions, and it should work, and it should give good results. So if you compare K epsilon ZF and K omega SST, you can clearly see the differences are really minor. Only one thing that I could spot is that in K zeta, he's giving more distinct these features of high shear stress, whereas in SST, I think he's smearing a little bit more on the helmet and on the shoulders. But overall, the values and the distribution, spatial distribution is almost the same. So, a few conclusions. Like I said, for proper turbulent treatment of wall-bounded flows, one needs a proper model. This proper model has to account for local and non-local effects, viscous or pressure related. And one needs to appropriately model the near wall region. In that respect, I'm putting forward a compound wall treatment, which implicitly combines either integration to the wall or far away standard wall function in a manner which doesn't explicitly depend on any parameter like y plus or some thickness or something like that. And lastly, in the model itself that I'm using, I've implemented a few details which can make a simulation stable, so that in case the mesh is too fine or too irregular, or for whatever reason, you get slowly from the zeta yielding zero wall boundary condition, and later when the flow is developed, to switch to more accurate result with n zeta 1. So here I come to the end of my talk, and I'll be glad to take any questions.
Just call one short question. Okay, thanks.
Thank you very much for your talk. I wonder, you mentioned about the near wall functions, but I can see lots of simulations can't ignore the near wall. I mean the boundary layer. So, like in the, what do you think the difference if we ignore this boundary, especially for, like my topic is about the force on the structure from the flow. So, what is the difference in the signal?
Well, I don't think you really ignore, but yeah, maybe we can talk more. Maybe you just put kinematic viscosity and that's it, without wall function, which would be this low Reynolds type of thing, whatever, which is inappropriate for the reason I explained. It's not reconstructing good the gradient. But if you have a external force dominant, then this is compensated. If the wall bounded flow is just driven by the pressure gradient, only thing that opposes is this wall shear stress. So if you don't have correct wall shear stress, you will simply push more than it should. But if there is something different, especially if you go to temperature effects and so on, then there are other things which are more important. And then this thing, even if it's not entirely correct, it's. So I suppose this is more or less the experience you're talking about.
Okay, yeah.
But we can talk about it.
Talk about in detail during the tea break. Okay.